Spanning trees are a particular type of tree which minimizes some measure of cost. So let's consider an example. Look at the graph on the screen here. This might be some type of network. So we have locations A, B, C, D, E, F. They have data connections. And this particular network has a lot of redundancy. So you could have at least one connection failing would not cause a problem. Possibly multiple connections failing would not cause a problem. So the goal with spanning trees is to reduce cost. Redundancy is nice, redundancy costs money. So we could ask the question, just how much can I simplify this network and still be able to send messages from any point to any other point? For example, if I wanted to send a message from A to D, I could send it across the top, I could send it through the bottom, I could zigzag around, go across the bottom. There are a lot of different ways to get messages between A and D. And so perhaps that's excessive. And we're going to minimize it in the sense of get rid of as much as we can. So let's try that on this graph. I'm going to start whittling away edges that maybe I don't need. Perhaps I'll take away the one in the lower right. No particular reason. There's a lot going on at that middle vertex, so how about I get rid of a lot of those edges? And now I have a tree. This is a connected graph, meaning that you can get from anywhere to anywhere else, and it has no cycles, meaning that if you pick a starting point and you start walking around, you can't get back to your starting point without repeating something. So this is called a spanning tree. It is a tree that spans all of the vertices. And spanning trees are not unique. Looking at this figure, I could have come up with many others. For example, I might take C as being special somehow. I'm going to have everything grow from there. So this is another spanning tree on this. So there may be many possible spanning trees. So let's make this a little more concrete. So suppose that you have a graph, G, that will be the one on the left here. Then a subgraph is what you get when you remove some of the vertices or edges. For example, maybe I wipe out this whole block on the right. And hey, might as well take out another edge. So this is a subgraph of the original because I started with the original graph and I removed some vertices and edges. More to our interest here, the subgraph is called a spanning subgraph if all of the original vertices are still there. So in this example, if I eliminated the diagonal, this would no longer be a spanning subgraph because one of the vertices was removed. Next, a spanning tree is a spanning subgraph that is also a tree. So I could have these graphs and maybe I get rid of some of the edges. Remember, I can't get rid of vertices because then it would not be a spanning subgraph. So I get rid of some edges. And here I have a spanning tree. As I said earlier, there are many possible spanning trees. One useful observation when forming a spanning tree is that we can use the edge and vertex relationship. The number of edges should be the number of vertices minus 1. So for example, in the two spanning trees you see here, each of those has 1, 2, 3, 4, 5, 6 vertices minus 1, and each of them has 5 edges. Looking on the right, same story, 5 edges, 6 vertices. And recall that this is a property of trees. If you have a connected graph where the number of edges and vertices have this relationship, then it is automatically a tree. Now, what if I throw in a little extra information? So I don't just have a tree with edges, but I actually have a tree with numbers on the edges. We call this a weighted graph. So this weighted graph here has all these numbers, and I might imagine that this is some measure of cost for my network. High cost ones, like that 5 on the top, are not as nice for the business as low cost ones like the 2. So your boss might come and say, we have all this redundancy, I want to save money, get rid of as much as you can, and make sure you give me the cheapest network. So this is called a minimum spanning tree, and sometimes called a minimal weight spanning tree. This will be taking the graph, we will be eliminating a bunch of edges to get a spanning tree, and we want the total weight remaining to be the smallest possible. For example, let's give this a try and see what we can come up with. Well, we decided that 5 is a bad idea, so let's get rid of that. And at the bottom, hey, there's another 5, but let's try to be creative, and maybe that 5 is useful because look, 4 plus 2 is 6, and that's more than 5. So this is a good way to connect E and F. How about I get rid of that 4 then instead? There's another 4. How about getting rid of that one? I'm doing pretty good. I almost have a tree, but I don't quite have one because there is a cycle. Okay, so get rid of one more edge to make that. How about this? 2 down here. This is actually a path. Path, recall, means I can just keep walking around and get to the end. So this is one possible spanning tree. And the total weight, the sum of the weights, we have 2, 3, 3, 3, and 5. So that's 16. Now let's try again. Look like I did pretty good, but I did say at the start that 5 seemed like they're not a good idea. So how about I get rid of both of those 5s? Do this on the bottom figure. Well, 4s are the next worst thing. How about I get rid of those? And hey, I have a spanning tree. It is connected, and there are no cycles. And recall that if you're ever lacking confidence about whether there are cycles, you can instead use the formula down here that says, just check the number of edges and vertices. So in this case, I would look at it and say, okay, I'm not very confident that there are no cycles, but I can count. So I count the vertices, and there are 6. And I count the edges, and there are 5. And lo and behold, the number of vertices was 1 plus the number of edges. And so it does appear that this must be a tree. In fact, not just it appears that way, but it must be true. Now, looking at that bottom figure, the total weight is smaller. If I add up the weights, on the far left, I have 2, 3, 3, 2, and 3. So that's 3, 6, 9, 11, 13. So we had 16 the first time, 13 the second time. So we're doing better. And of course, we might ask, well, can you do even better than this? Is this the minimal spanning tree? And maybe it is. But if you try again, maybe you're going to beat it 13. So given the uncertainty, it's good to have an algorithm that we know works. And the algorithm we're going to be learning is called Prim's algorithm. It's a fairly simple algorithm, and it is guaranteed to give you a minimal spanning tree. It's not necessarily the case that this would be the one that's most aesthetically pleasing, but it will minimize the total weight of all the edges. So let's see how that works. So I'm going to look at the same graph that we saw earlier. And I'm going to start with all the vertices, but none of the edges. So let's draw those vertices. Those are A, B, C, D, E, and F. And then it says choose a starting vertex. Any vertex is okay. So, okay, A is a nice letter of the alphabet, so why not start there? So I'm starting at A. Step 3, add a vertex from R complement. And what does that mean? Well, R are the vertices I have added so far. Initially, it's just A. I want one from R complement that has the cheapest connection coming back. So there are 3 ways to get there. I have a 2, a 3, and a 5. So the cheapest one would be that bottom one, that 2. So let's do it. Now I added a vertex, so let me highlight that one too. Repeat until there's nothing left over. So, okay, let's look at these. What do we have that we could add at this point? I'll use a different color. So we have a 4, or a 5, or there was that 3, or a 5. So those are my choices of where I can go from those blue points. Well, the 3 is the cheapest, so let's do that one. Now I have added that new point. So there we go. And we repeat. Just keep on doing this process. So I throw in all the edges and I look at which one forms the cheapest connection. So I could go here, which is a 5. Here is a 3, 2. Let me comment on some of these edges here. Okay, well, I put this 4 down at the bottom, but that 4 does not connect to R complement to R. So that one shouldn't have been added. So don't do that one because it says I'm adding a vertex from R complement. That means the things that aren't blue. Okay, so I don't do that, but I can do that bottom one here because I was adding F, right? I added F, I've added B. Those are both in the complement. Okay, what's the cheapest? I have that 2, so the 2 is the cheapest. Okay, now we're continuing this process. I can go to either B or D. So I'll throw in all the possible edges. I could connect by a 5, by a 3, by a 3. Notice I did not put the edge in between there because that is not connecting the blue dots to the not blue dots, R complement to R. So I have a tie. 2 3s are possible here. And you can take your pick. There are different modifications in this algorithm that might do things like lower the diameter, but we're just learning it the first time. We don't care about that. So I'll put the middle 3 in because it just looks nicer. Okay, so middle 3. Now I grow my R community. There's only one place left to go. I could go down at the top, a 4, or the lower right, a 3. What's the cheapest cost? The 3. So I connect that. And now I have, let's see, keep doing it until there are no vertices left. Well, I've done it. All of the things are marked in blue. So the algorithm is done, and we are guaranteed that this gives a minimum weight spanning tree. So let's add these up and see what the total cost was. This will help us figure out if that earlier attempt gave the best answer. So add up all the weights. That'll be 2, 3, 3, 2, 3. Well, that's 5, 8, 10, 13. So the minimum cost possible is 13. And looking back here, well, actually, that was the exact same answer. So we had 13 before, 13 again. So pretty good. Now recall there were ties along the way. So there is the possibility that more than one answer will be correct. However, any trees that you get will have the minimum weight of 13 in this case. So if somebody uses the algorithm and they get a 14, they made a mistake. If they get a 13, but their tree is different than yours, that could be just fine.